All right, so this week and well, the next few weeks here, we're going to be talking about closed loop systems. So the this is actually in your book. Okay, we're in chapter 12 of your book here. So if you have your books, you may want to read through this. But we're just going to kind of go through and do some definitions here and then talk about the differences between open and closed loop. Okay. So first of all, automation is a sophisticated control system that self-regulates a process parameter with reduced or limited human intervention, right? So this means that we're going to have the system is going to perform a task, and it's going to kind of monitor itself and make adjustments as it needs to. And really, I mean, that's kind of what the PLCs are all about. All right, now the big thing here that we're going to be looking at is we're going to set a point. So this is something that, you know, the human, the operator is going to set the operation point, and then we're going to use sensors, analog sensors, transducers, to monitor the actual output of the system, feed that back, and that feedback, you take your set point minus the feedback, and that's going to give us an error. That's going to, you know, the difference between where we want to be and where we actually are. Okay, so the error here is where we want to be, or the difference between where we want to be, which is the set point, and where the system is actually at. So once we know this error, we can now use that to adjust our control to push the system in the direction that we want. All right. So we really, there's kind of two type of control systems, and so far, like most of everything we've been doing is been open loop control. Now if you remember back in the PLC1 class, we did one lab with like the sensors and that sort of had some closed loop, but it was not very fine. Okay, it was kind of coarse control. But we're going to concentrate here, like I say, for the rest of the semester on this concept of closing the loop here. All right, so an open loop signal, we have no feedback. We have no sensor, or we might have a sensor monitoring where the system's at, but we're not feeding it back in to make adjustments. So an example of this, we use a lot of times when control systems, we have block diagrams that we kind of use to show the different parts of the system. So for the open loop system here, all right, so here for this open loop system, we want to push the system. So we generate a command, and we send that command to the controller, meaning like, it might be something like we tell it we want it to run at a certain speed. Okay, so we may like set a speed inside of our HMI or something like that and say we want you to run at 300 RPMs, and then the controller generates a control output, which converts that into the 4 to 20 milliamp signal or whatever. Then it sends that down to the servo motor to run at that speed or to move to a certain position or whatever the case may be. All right, but there's nothing in here that's telling us that did it actually get to that speed or that position. So a very common household system that you see with this is something like your dryer. So you have your dryer, you set the timer, you put some clothes in the dryer, and you set the timer on the dryer and say, I want you to run for 30 minutes. And the dryer turns on, it heats up, it's, rotates around. And then the clothes are the process, which we're actually trying to get the clothes dry. And at the end of the timer, when the timer goes off, then we open the door and we pull out the clothes and we see how dry they are. Right? So there's nothing in there stating how monitoring how dry the clothes are. It's just, you set the timer, you run it until the timer expires, then you open up the door and see what the result was. Okay, that's open loop. All right, now on a closed loop system, then we can take a transducer, right, some analog sensor, and we can monitor that and feed that value back in here. Okay, so to do that, we're going to have some different parts here. I'll just talk about them over here. So here is the closed loop system for the dryer. And so what we have here is we have our set point. So instead of just saying run for 30 minutes, we tell it how much moisture we want to be in the clothes when we're done. Do you want the 10% moisture, 5% moisture? You put in there more of a dryness setting instead of just a time. And then here, this is what we call the summing junction. This is really supposed to be kind of like a plus sign here. This is a summing junction. And so what we're going to do is we have a sensor inside the dryer that is measuring the actual moisture content within the dryer. And so given that, then we measure what the actual moisture is. And, so actually in this block diagram, here's the sensor, but we're measuring that moisture content and feeding that back. And so now we have this error signal where, again, the error is the set point value, the amount of moisture we want in the clothes minus what the sensor is telling us is actually in the clothes, and that gives us the error. All right, so now we have the error, and then we feed the error into our controller, and our controller decides, hey, I still need to run, so I'm going to send out I'm going to send out an output instruction to the heating element. So if my sensor is reporting that there's still a lot of humidity, then I'm going to make sure, that I have a lot of heat. And so I'm going to turn up the voltage to heat up the elements, or I'm just going to continue running. Maybe I'm not going to heat it any hotter, but I'm going to, run it a little bit longer, whatever the case might be there. But, and so we're going to work on drying the clothes. And then we monitor this constantly. All right, so we might do this. We might use like a delta T timer, kind of like we use for the integrator, and only do it, once a minute or something, and make the adjustment. Or we may monitor it every scan of the PLC. And a lot of times you're really probably going to do at least some of it every scan. Every scan, as part of your input, you look at the sensor and say, hey, are the clothes dry yet? And if they are, stop the dryer. But if they're not, keep running. Right? And so it's this feedback piece right here that's the most important. Now, one thing I want to point out here is this negative sign. This is what we call negative feedback. Okay? So what we're looking at, the error is the difference between where we want to be and where we actually are. So you have to use negative feedback. You have to generate the difference. If you use positive feedback, that's just going to mess the system up, because you're telling the sensor saying, hey, the clothes are dry, and you're saying, well, heat them up more. All right. And so you don't want to do that. So you have to use the negative feedback and the error signal. So positive feedback will tend to just drive the system out of control, and to the point where the clothes get so dry they catch on fire or something. So you must use negative feedback. So you're looking at the difference between the set point and the error. All right, so what are the advantages of a closed loop system then? Why do we want to do this? Well, since we're going to be monitoring the state of the process, right, then number one, we're, the result should be much, much better than a standard open loop system, where it's just kind of like, okay, well, I threw these clothes in the dryer for 30 minutes, and certain types of clothes, maybe especially if it was a small load, 30 minutes they got too dry and all staticky, and maybe ruined some of them if they were delicate clothes. On the other hand, if you had like some big heavy stuff in there, like a blanket or something, and you put it in for 30 minutes and it's not even done. So with the closed loop system, right, you have it's self-regulating, it's monitoring it, and so you don't have to worry about it. You just tell it what humidity or what amount of moisture you want in them clothes, and the control system is going to do the rest. So we don't have to sit there and babysit it and hope that it does a nice job. And, we can, of course, adjust the set point. And all we have to do for the control system, if we go back to my diagram here for a minute, all right, so if we adjust the set point here, so that we say, well, these particular clothes, I want them to be, I don't want them to get quite so dry, or I want them drier than normal or something. I can adjust this. All I have to do is adjust the set point, and the controller will take care of the rest. So I don't have to worry about the other aspects of it. So the system is going to change automatically. Now, the other advantage is the fact that, let's say that the dryer has been running for a while, and you have all these clothes in there, and they're say they're like 3/4 dry, and then all of a sudden you look in the washer and you realize that you forgot one pair of jeans or something, and so you're like, now what am I going to do if I throw them into the dryer now? What's going to happen? Well, now you're throwing something that's very wet into a bunch of clothes that were almost dry. Okay. And so if you were just doing like the standard timer thing, when you do that, then obviously, it only had, 7 minutes to go or whatever, and then it stops, and all the clothes are still quite damp. But with this closed loop system, when you throw in that last pair of jeans that you forgot to put in, right, that's going to affect all the clothes in there, because some of that moisture from that wet pair of jeans is going to get, as the dryer runs, is going to get mixed in with everything else. But the sensor is going to sense that hey, there's more moisture in here, and so the controller is going to continue running until it removes all that moisture. All right, so that by throwing in those that last pair of jeans late, that would be what we would call a disturbance to the system. So the system was there and it's running, and it was And it was like, hey, life is good, man. I'm almost done with this job. And then all of a sudden, boom, hey, here's this soaking wet pair of jeans we threw in. But the controller's like, oh, okay, no problem. And it just continues on, and it'll cruise on and run longer as it needs to get the moisture out to get to the set point. Now, there are some disadvantages with the closed loop system. Number one disadvantage is it becomes much more expensive. We have to have a sensor in there. We have to have a smart controller that can, I mean, you know, we have to have a controller in there that's more than just a timer anyhow, so that it has, you know, it's going to may have more parts, number one. It may take more time to set up. You know, if the sensor goes bad, you know, that was something that wouldn't have went bad before because we didn't have a sensor. So there's, you know, more expensive, possibly more downtime. It's a more complex system. We're going to have to program this. And the system can cause instabilities. Okay, so the instabilities can come from many different sources. The number one source of instability is the delay. Now remember, with a PLC, you have a scan time. And so you have, you know, it's going to, the scan of a PLC, it first reads the inputs, then it runs through all of the ladder logic or program, whether it's function blocks or ladder logic or, you know, structured text or some combination of all those. And it runs through all that code. It does its system checks, and then it sends out the output. That's when it's going to send out the new control. Well, there's a delay in there. Now, the modern PLCs, you know, are pretty fast, but still that delay could be, you know, maybe 10 milliseconds or something, depending on the size of your program and other aspects. And so there's an inherent delay in a closed loop system using a PLC or any sort of digital computer, because you have to, as I said again, your scan, think about your scan. You have to read in the values, then you run through all the code, do all your system checks, then you send your output. And there's that delay between when you sensed how much moisture was in the clothes and when you actually send out a new instruction. And so that delay can cause or add to the possibility of the system going unstable. Another aspect of instability comes from noise in the system. So when we talked way back in week 1, we talked about the various different types of noise and interference, and we talked about crosstalk inside of a cable, and, you know, noise from radio signals or cell signals, and, you know, noise from motors running or other equipment running. All right, any kind of noise that's injected into your signal, and, you know, in there, that's going to confuse your controller, and so that could add to instability. The other one is gain. Okay, so if you think about gain, we haven't discussed gain too much yet. We will get into it more here. But as you try to make the controller run faster, move faster, start up or react faster, that is by adding gain. And so when you you know, if you increase the gain, that'll make it react faster due to the noises and, you know, inaccuracies in the system. And you guys have seen that with our PLCs, right? As we're reading these load cells and things, and you see how those numbers bounce around so much. And then, you know, you think about, hey, you know, you were supposed to, it was sending out a 16 milliamp signal, and all of a sudden signal from the sensor from the load cell jump from 16 milliamps to 18 milliamps. And then you multiply that. If your gain, let's say you're using a gain of 10, you multiply that by 10, right? Now you've just went up, 20 milliamps, and after you're scaling or whatever, what that is, but this gain makes it respond even more to that noise. And so the more gain in the system, the better, larger chance that your system's going to go unstable. All right, so I already talked about adding more clothes to the dryer, okay, as a disturbance. So, as I said before, your process disturbance, okay, I used the example here where we threw in more wet clothes into the dryer, but this slide here is just talking about some general places where these disturbances could come from. So number one, you get a current inrush. When you first turn on any electrical equipment, if you remember capacitors, when you have a discharged capacitor, it tends to draw in a lot of current initially. That current dies down fairly quickly, but you get this large inrush. And so, most electronic equipment is going to have some capacitors in there. Electric motors, remember inductors kind of act like a short circuit. So, and in electric motors are actually basically big inductors. And when you first turn them on, they just look like a bunch of copper wire, right? So they just look like a short circuit until the motor actually starts running and starts spinning. You get that huge inrush of current. So either of those sorts of examples can generate a large inrush of current, which would be a disturbance to your control system as you're turning something on or off or whatever. It's going to add a disturbance. Vibrations, and if you're like measuring the speed of something, rotating or something like that, or any kind of vibrations will throw off your measurements, and that would be a disturbance. Any speed variance, just if you're trying to measure, say, air pressure or pressure inside of a system, and somebody opens a door or valve or something and lets some air in or out or whatever, that's going to disturb the system. Mechanical wear, right? You have belts and pulleys and gears and things. Those things will wear down, and so you get more when you kind of start and stop things, you get this kind of slop or delay and then a jolt in there. So all these kind of different things could and do result in disturbances into your system. All right, so this slide is just kind of talking about what they call the direct and the reverse acting controllers. All right, so I've already kind of talked about it. And by the way, just as a reference, if you got your book there, right? This is on page 401 of your second edition of the reg book, the PLC book. But we have here our set point. It just says input in this case, but this is our set point value. And here's our feedback. And now here I do have the plus sign and negative sign. All right, so our input is a positive value and our feedback is negative, which of course, as I stated before, gives us our negative feedback to generate the error. However, we can do direct or reverse acting control. And the difference is basically, do you take the set point minus the process variable? What they're calling the process variable here is your feedback. Okay, so the process variable, right, that is your humidity in the clothes dryer or whatever, that your sensor, your transducer is reading that value and feeding that back. So that's why they're using the term process variable here. All right, so if your set point is positive and your feedback is negative, you're using a negative sign here. Remember, this circle with the X in it is what we call the summing junction. It adds these two together. All right. So, but you know, this gives us our standard error where we have the set point minus the process variable. Now in this lower equation here, I have E is the error, and then this T value here represents time. So this is just kind of showing us that, you know, this system, which any control system, is going to be dependent on time, because as your sensor is feeding back different values at different times, then your error is going to change with time. So that's why this is just kind of showing time dependence here. All right, now you could actually flip it the other way, and you could have your process variable be positive, but then you have to negate your set point. Okay, so you negate that set point, and that gives you the error then. All right, and so that's the difference between the direct and the reverse acting. So let's take a look sort of how this applies. So here is a control system, and the idea is that we want to, our set point is going to be this desired level in this tank. Okay, so we want to put this liquid into this tank, which is actually what we're going to be doing here later in a week or two here, probably not next week, but the following week. We're actually going to take our control system and hook it up to those water tanks in the back of the room. All right, and so we're going to set a desired level. Now we have a sensor here, and the sensor, of course, is just measuring this desired level. We have a valve which is controlling the water coming in, and then we have the water is leaving the tank. Okay, so you know the water is being removed from the tank, but we want to keep the tank at such a given level. And so this is what they call reverse acting here, because if the process variable decreases, your error is going to increase. Okay, and so so you have to actually open the valve more. All right, so you have to open the valve more so that the level will be maintained. All right, and it's actually the opening of the valve more. As this, your process variable is going down, and your valve has to open more. That's the reverse acting piece. Okay, that's why it's called reverse acting. Now, on the other hand, if we put the valve down here on the drain, then as the error increases, then you have to, so as your error increases from your desired level, then you have to open the valve more. Okay, and so that's why they call it direct acting. So it's kind of the difference between reverse and direct acting is basically where you're putting your controller. See, the valve here is our control in this particular system, right? We can open or close the valve more or less, and so that's our control. So the question is the control up here, is our control up here, or is the control down here. All right, and that's the difference between the direct acting, and it's kind of basically where is your control at. All right, so there's just the two of them thrown together on the same slide so that you can see, you know, we're doing the same thing. We're trying to maintain the level in this tank, but the difference is where our control is at. All right, so here is a closed loop system that was invented by James Watt. Now, if you remember James Watt, he's the guy, when we talk about power in electrical circuits, we use the watt, okay? Same guy here, he did a lot of mechanical stuff too, and he invented the fly ball governor. And this was just, you know, this was a total mechanical uh, closed loop system that he built. All right. And technically, this is also known as an analog system. All right. So this is an analog system. And what I mean by analog is it doesn't have that built-in delay that our PLCs have. Because if the system changes, right, this system changes immediately. Okay, there's no delay. We don't have to wait to read the inputs, run the ladder logic, and generate the output. So the way this works is you have your valve over here. You have this valve, and we've got a mechanical arm attached to this lever. And then we have this these weighted balls here on this spinning, right? So this here steam engine is going to be causing the steam engine is going to be turning, right? So it's going to be turning a wheel. I guess this is the wheel here in this picture over here. And it's going to be turning this wheel. And so what we've got is we've got this mechanism here. It looks almost like a pair of pliers or scissors or something, with these weights down here at the bottom. And as you know, as you spin around a heavy weight, the faster you spin it, these things move further and further out, right? The inertia, as you're spinning it around, the inertia makes these fly out. But the scissor action brings this lever down. And if this lever goes down, then this lever over here goes up, which closes the valve, which slows down the system. All right. And when the system starts slowing down too much, let's say you put a load on it and it starts bogging down, so you need more, the weights start moving back in because it's slowing down. And so when they move back in, they push this lever up, and then that makes this lever go down, which opens this valve over here. So this is just, you know, an ingenious way of controlling the speed of this engine. And we didn't need no, you know, James Watt didn't have a PLC back then. He didn't have servo motors or 4 to 20 milliamp sensors and actuators, right? But he built this total mechanical thing, and you know, it works very, very well. And in some ways, it actually works better than a PLC would because of that inherent delay in the PLC. All right, and so I mean, most of the time, a PLC, you know, we could do some kind of control like this to using a PLC, and it would not go unstable. But remember that with that delay, you do have to be careful that if that delay is too long, you could add some severe instabilities into the system, where the system, you know, instead of the system moving nice and smoothly, it starts reacting kind of violently to any disturbance in there. All right. But so this is the closed loop system here. And like I say, this one, you know, completely mechanical, invented in 1775. All right, so here's an example of a mechanical closed loop system, kind of similar to what we were talking about, but this is actually the example of your standard like toilet in your house. And so what we have here is we have a float valve, and so it's basically got this sort of triangular sort of plunger in here that'll open or shut the water off. Okay, and so what happens is when you drain this, so you open this up and allow the water to leave, then the lever, the lever for the float, the float drops, which pulls this lever down, which of course allows water to return into the system. And then as the water level rises, the water slows down, so you don't leave in as much water, right? As it starts to get close to full, then very little water, and only just a little bit of water will come in here. So it'll run slower until it gets to the point that it's fully up, and then the plug is in there and fully shuts off the water. Okay. Now here's more of an industrial application. And so in this industrial application here now, we have a storage hopper where we have some aggregate here. I believe this was actually a model from for salt. So what we have here is like a bunch of salt, and inside of this hopper, and then we have this conveyor. So what we're doing is we're running this down here, and we have a level probe here to measure the height in this funnel. And so we need to maintain, what we're trying to do here is like fill bags. Let's say this is filling the bags of salt for your that you would go to the store and buy salt for your water softener or something like that. So you have this salt is flowing down here into the bag, and we need this to flow at a constant rate so that we know exactly how much is falling through there. And so that's based on this level, because if the level gets too high, you have more weight, it's going to push it out faster, right? Gravity is going to pull it out faster. So we want to maintain this constant level at what they're saying here, 40% full. And so we have the probe as our sensor, right? We have this level probe, which is our sensor or transducer, which is going to, looks like sending down either an ultrasonic or laser signal down here to measure the height, and then send our 4 to 20 milliamp signal over to a variable frequency drive. And so we send this 4 to 20 milliamp signal into this controller, this VFD, variable frequency drive controller, which changes the frequency to the motor, which is how we control the speed of an AC motor, by changing the frequency. So if we change the frequency, we can make the motor run faster or slower based on the information from the probe. Okay. So there's, like I say, a more industrial sort of application here. Here is another sort of industrial application. This one's a little bit more involved here, because this is for a robotic servo arm. And we're going to be controlling two different things here. When we talk about robots, we obviously have to control the position of the robot arm, but we also want to control the speed of that robot arm. So it's the exact same thing. The only difference here is we have to actually have two sensors. So we have to have a speed sensor and a position sensor. We're going to feed the speed into this comparator and generate a velocity error. And then we're going to feed the position into this comparator and generate an angle or position error. There's use an angle because we're talking about the, most robots, especially the articulated robots, have a, you have the joint, they're rotational joints. And so that's why they're talking about the joint angle to tell us the position. So we're looking at the position angle of the joint. All right, so here we have two errors, and we're feeding both of those errors up here into what they call the actuator driver, but this is actually like our controller piece. Actually, this whole dotted rectangle here is the controller. So this is all happening inside the controller. And so we're inside the controller, we have this comparator here is our summing junction for the velocity. We have the actual velocity, and then we have the set point where we want it to be at. And then this is the summing junction for the angle. So we have our set point angle where we want it to be, and we have our actual where it's currently at. And then so inside of here, like I say, this whole thing is inside the robot controller. So when they feed this into the driver, they're actually telling it what's, do I speed up? Do I slow down? What should I be doing? And then it sends those back out to the servo motor. Okay. All right, so here's just, again, the block diagram here of our system. And what I wanted to kind of point out here was that, as I just did on the other slide, actually, this is the summing junction. Now, the summing junction for us is going to be right inside our PLC controller. All right, so we're going to have a set point that we set, which could be inside of the PLC, or once we build an HMI using our factory talk or whatever, and we build the HMI, we're going to put the set point inside the HMI. And then the operator can change the set point at any time. And so the set point is going to be fed in through our HMI into the controller, the PLC. And of course, we have our sensors, one or more sensors here, converting and feeding that in to our analog input. Now our controller is calculating the error, okay? And this here is simply an add block, okay? Or actually, we'll probably end up just simply doing it in a compute statement. But, you're calculating your error, which is your set point minus, don't forget the negative sign, minus your feedback. Now you have your error. So you could either use it with a subtraction block, or you could do it, if you're doing like standard proportional control, you could just do it all inside of one compute statement. All right, and so then this is your control. This is your ladder logic or your function block diagram. You're calculating what to do. You're looking at your error and saying, hey, I've got a lot of error, I got a little error, maybe I have no error at all. What do I send out? Okay, so this here is inside your PLC. This red box is your PLC, and this is where you're going to decide, what do I send out to my system? And so this is your analog output here now. So we've only used the analog output maybe once or twice, but now we're going to use it because we're going to use our analog input over here, compare that to the set point, generate our error, apply logic to this, and then take that logic, feed that out to our actuator. So this where it says control elements, these are our actuators. And then the actuators then are actually going to control what the plant is doing. The plant is just our system. Plant is just another term for system. And then here shows the disturbance. Now sometimes we'll show a disturbance over here with a summing junction. In this case, we're showing it just, this is the disturbance coming right into the plant. And like I say, this could be, you know, any kind of the disturbances that we've already talked about that is going to confuse up the system. All right, so I guess I pretty much already talked about all on this slide. Is just kind of labeling everything I just said in the previous slide. All right, so the output is the variable that we're going to manipulate, and we're going to use ladder logic or possibly function block diagrams or some other sort of program inside of our PLC or our computer to look at the error between our set point and our process variable and calculate, okay, what do I do now? All right, so that, and then we're going to generate this output, which is going to come out our analog out. All right, so it'll probably be a 4 to 20 milliamp signal. It could be a 0 to 10 volt signal if we want to use a voltage out, but we're going to generate that output signal and then send that then into our system. Okay, and as I said before, the plant is the system that you're trying to control, whether it was the dryer or the water level in a toilet or the hoppers or whatever. That's the system that we're trying to control. And so the disturbances, we talked about that. The feedback, right, that's our analog sensor. Electrical transducer, feedback element, these are all fancy terms for our sensor. Okay, so now our feedback signals, they could be pneumatic. Okay, so we could use a pneumatic feedback, but we really don't like these because air can be compressed, which results in slow reaction times, number one, plus you can get like shock waves or pulses bouncing through the air system, which will increase disturbance. All right, so you know, years ago when electrical sensors and things weren't quite so cheap and reliable, they used to use these type of control systems, but nowadays you probably won't see a pneumatic control system. All right, mechanical linkage ones, well, we already saw that with James Watt's flyball governor. And, you know, these work really nice in certain applications. They will wear because, you know, they have bearings or whatever in them and other aspects that they may get wear in them, and that will, after they wear out a little bit, they might not perform quite as well as they did when they were new. Okay, but you know, but when they're in good working order, they're very simple, and in a lot of ways they're much simpler than trying to use a PLC or something to get it to work, and it just works and you don't have to worry about it until it wears out. All right, but on the other hand, it's limited to what it can do. Okay, they do work, they do some nice jobs, but they also have some limitations because you can't make changes to them rapidly. You can't program them for multiple different uses or things like that very easily. Okay. Then we have our digital electronic, which basically for us is our PLC. All right, and so we have to convert an analog signal into a binary number, and then, which is what the analog to digital converters do, right? So the analog to digital converter is going to take the analog value from the sensor, the 420 milliamps or 0 to 10 volts or whatever, and send that into our actual and send that into our controller, into our ladder logic. Then we're going to execute the ladder logic. Right? Or it could be function blocks, or, whatever programming language you're using for that. And then we're going to run it into a digital to analog converter back out as our output. All right. So this would be the analog full control. Now, on the other hand, we could use discrete on or off, which is what you did back in the PLC1 class. If you remember that, and you used a couple of different sensors to kind of mimic this level of water in a tank. And it was just kind of what we call a bang bang control. So the pump didn't turn on until the water dropped below the low level, but then the pump stays on until it gets up above, or at least to the high level mark. So this was just below the low value. We turn the pump on, right? And the pump stays on until it reaches the high level. Till the high level sensor tells us that it's all the way full. All right, and so that would be the discrete. Discrete will work for certain types of jobs, but the analog will give us constant monitoring of the system and react constantly. So we can change the speed as the level increases or decreases, or whatever the case is. We can make continuous adjustments to that. All right. And then there's also, we can actually do analog we can build an electronic circuit using op amps, which generates an analog control signal. And we used to do this in the class, but we kind of don't have time anymore because of some of the other things we've added into the class. But with using these op amps, operational amplifiers, we can build a relatively simple circuit that can provide closed loop control using just electricity, and we don't have to use a PLC. So, if you've ever worked with an op amp, they have like what they call the 741 op amp, which is kind of like the standard op amp. These things cost about, I don't know, 20 cents a piece if you buy them in bulk of 1,000 or something like that, which you probably don't, but still they're extremely cheap. So with a couple of op amps and a few resistors and capacitors, you could build a control system that was an electronic control system for, maybe, $20 or something. Extremely cheap. And you could build yourself this little electronic control system, and you don't actually have to go out and buy a PLC and program a PLC and all that. But again, these things are kind of limited, kind of like the mechanical one, where the PLC, it gives you a lot of options. Plus, you could use it to actually control lots of different systems simultaneously. Where like this system here, you would have to, if you had two different systems you wanted to control, you'd have to build a second one for the second system. and so on. But with the PLC, right, you would just have to add some more ladder logic and, you know, wire up the other sensors for the other system. Okay. So, but there is that possibility if you just need a cheap, low cost, fairly fundamental controller, then you could do that with op amps. All right, so just kind of looking at this, okay, the controller compares the instantaneous reading to the set point. Now, I'm reading that, and that may not be quite accurate. It is reading the instantaneous value at the scan time. So remember, when we do our scan, we come through and we read our inputs. So at the time that we read the inputs, the set point is compared to the feedback value from our sensor instantaneously, which means, you know, when that scan is at that, we're reading that value right now. Okay, but there will be a delay before we generate our output. All right, so our final control element is also known as an actuator, right? And I think we talked at least a little bit about these before, but this final control element here is something that we're gonna feed in out of our analog output, and we're gonna send out a 4 to 20 milliamp signal or 0 to 10 volt signal to this device, which in this case, this is a valve. And so we're going to send this 4 to 20 milliamp signal here into the electrical box of this valve. And then it's going to use that then to decide how far does it open or close the flow valve to allow, you know, things to move through it. Now, for our water tank, this is actually our flow control valve in the water tank. So, I mean, we're not in the classroom at the moment, but when we get there, you'll see these, right? You know, if you go in there like next week and you can walk to the back of the room there and look at those tanks, and I can say, we'll actually get them out the following week and wire up our PLCs to these things. And these take a 4 to 20 milliamp signal in here. And then we it just opens or shuts this valve, which allows the water to flow through. Down here is where we hook up the water line to it, and allows the water to run through that, so we can control how much water is flowing through. So we actually have a pump down in the tank that's going to pump water, but it can't pump all the water, because if the valve's shut, then, you know, water can't flow through there. And so as we open the valve a little bit of water will come through, and if we open the valve all the way, a lot of water comes through. But that's our control elements. All right, now a lot of times when we're talking about these, we'll see this I/P, which means current to pneumatic transducer. So like this valve up here it's actually generating its pressure, and it's pushing down there. It puts pressure in this can up here. This is a pressure tank, and as the pressure increases, there's a diaphragm in here which pushes the valve down to close the valve, or push the air in the opposite direction to push the valve up to open the valve. All right. All right, so when we're going to program this in our PLC, okay, the first thing we have to do is read in our input, right, from our process variable, and we may have to scale it, because remember, technically our process variable might be pressure, or it might be, the level of water in the tank, or it might be a voltage or whatever, but then it's going to be converted into like a 4 to 20 milliamp signal, or a 0 to 10 volt signal, analog signal. It's going to come into our PLC and be converted into a binary number. Well, what does that binary number mean? How many gallons are in the tank, or whatever? So we're going to have to read in this variable, and we'll have to, of course, scale it if necessary. All right, and then we'll compare the variable with the set point right here at the summing junction, and then we'll look at the error, right? We have the error right there, and then we're going to decide, what do we do now? So what kind of output, how are we going to change our output based on our error? Okay, so that's kind of the way that we're going to do this. Okay, this slide's just kind of a repeat here. All right, so in our control loop, we have our sensor, which is reading the process variable, and it's then converting that and transmitting that into the controller, the PLC. The controller then is going to calculate the error and execute the ladder logic to determine what output to send to the actuator, and then it's going to send that to the actuator. All right, so here's an example for a cruise control in a car. All right, so we have our cruise control in our car. So and they're using R here as reference and S to be the system. Okay, so that's where the R and S come from. I think this, if I remember right, this actually came right out of your book here. This is an example right out of the book. So he used those letters. So the set point, or our reference point, is going to be how fast we want the car to be driving. And then this is the actual speed. Actually, I guess speed in this case is, you can think of either S to be the system or the current speed, but it's going to be miles per hour, right? And so we're feeding that into our controller. So remember, technically, right? Technically, this whole piece here is the controller. So the summing junction is actually inside the controller. It's just an add block or a compute statement inside of our ladder logic. Okay. And then we're going to decide what to do based on that error. Okay. So we're going to decide what to do based on that error. And then we're going to, sorry, the phone's been ringing off the hook today. We're going to feed that into our system then. Now, the problem is, if this is a cruise control in our car, a good example of disturbance is when you start going up a hill, right? So as you start going up a hill, they're using G for grade here, then your car is going to start slowing down. And so this is the disturbance into this extra summing junction here. All right, so I have the second summing junction is showing you the disturbance. And that's going to cause you to slow down, okay, which is why there's a negative sign. It's coming in as a negative because it's going up the hill would be slowing it down. And so, but the beauty of this, again, is the fact that even though technically the controller doesn't see that we're going up the hill, but it does see that we slowed down because of this feedback. And so therefore, as the speed of the car slows down, we feed this back in and we see that the error between the speed that we want to be going and we're actually going has increased. And so the error has increased. And so therefore we need to increase our throttle so we can go faster to maintain our desired speed, right? Because we've already slowed down because of the disturbance. And that's the, again, that's the idea of any sort of closed loop system, is we want to be able to react to any disturbance in the system. All right, so if we are going to do this in one of the most simplest controls is what we call proportional control. Okay, so proportional can't spell today. Proportional control is really, really easy. Okay, it's so, I can't spell, but if I could spell proportional control here, if I was going to program this into my PLC, I need one compute statement. Okay, that compute statement would basically be, I would have to scale in. I mean, before the control statement, I probably have to scale my process variable back into miles per hour or whatever. But I would take the error. Okay, your error is your set point minus your actual value. So I'd have my scaled speed, so I'd scale it back in, because remember, coming in as a process variable, coming in from the sensor, it's a 4 to 20 milliamp signal or 0 to 10 volt system. It's not 55 miles an hour, right? And so I have to scale it. So I have to have a compute statement to scale it back to the scaled value, all right? But then this is my error. So what I have right here is my error. Set point minus my scaled speed. Now I'm going to multiply that times a gain. That is my control. Okay, that is what we call proportional control. It's effectively one compute statement inside of your ladder logic. It's so easy. Now, the only thing is with this gain is just a number, 5, 10, 15, 0.1. Remember, you don't want your gain to be too large. Okay, you want, because too large of a gain will number one, it will kind of waste energy, right? So if you think about driving in a car and you come to a hill and you slow down, so you want to get back up to speed and you don't have cruise control set, you just floor it, right? If you just boom step on the throttle, now you're really using way more gas than you needed to get up to speed faster. And so number one, that's wasteful. It's wasting energy. It's wasting gasoline in this example. But number two is now it kind of makes it a little bit unstable. So you get to the top of the hill and you still got your foot floored down, throttled down to the floor. And now you lit up on the gas, but as soon as you top that hill, there's a cop, with his radar, right? And you get busted, right? So we don't want that either. So because you're actually going too fast, and then you try to slow down and things like that. So it's very inefficient if you make your gain too high, but it can also make it unstable. But this gain is basically just a number. You get to pick it. So beauty is we can change it either inside the controller. We can make gain a tag inside of our RS Logix 5000 or whatever software we're using, and then we can change it, or we can build an HMI and we can change it in the HMI so that we can adjust this gain. Now, on Wednesday, I'm going to do another lecture, which is going to talk about how to, how this gain can affects our response. Okay, so we're going to look at the response of closed loop systems next week, next class, which is going to be Wednesday. So I will be doing this live again if you guys are available and you want to log in. Okay, but that's pretty much it for today. But like I say, for proportional control on this Wednesday, yes, Brandon. Okay, but this proportional control is so trivially easy to do, and it does a pretty nice job. I mean, if you wanted to do it really easy, you could just set the gain to 1, okay? And so basically it's not even there. So you just take your error and then you feed your error, and then you have to, of course, scale it back out to go back out. But it's just very, very easy to do proportional control. So yeah, I will cover that. And the first thing that we're going to do next week is we're going to do some proportional control. Unfortunately, I probably won't be there, but at least not on Tuesday. But I have you do some proportional control on a RLC circuit, and I'll talk about that in a lecture too. But that's all I have for today. That proportional control, I hope you didn't do it yet. We just talked about it today. I need to change the date. We're like a week behind where my schedule said we should be. So yeah, so I'll be changing the due date on that. And I will post the lecture if I forget. If you don't see it out there, come out by, later tonight, email me and let me know and I'll get it out there. But problem is I have to wait for it. It takes about an hour for Blackboard to prepare it so I could actually post it. All right, any other questions there? Okay, well, you guys know you can shoot me an email or something if you have any questions. I think my system just locked. I don't know if you can still hear me, but my system's hung.